using symmetry to our advantage. Okay. Even functions. So function negative x is equal to function x. Now we've seen we can change this nicely by using the symmetry. Instead of integrating from minus a to a, we can go twice 0 to a. But should the situation arise, if we've got an even curve that has been shifted, and you happen to notice that, but you have symmetry around where it's been shifted to. So say we've moved it over to x equals c, but we're integrating from c minus a to c plus a, then we could still use that idea. We're still going to have symmetry about c equals a. Yes, it's an unusual situation. You may never use it. But if you do happen to spot it, use it to your advantage. Similarly with odd functions, remember function negative x is equal to negative function x. That meant the integral from minus a to a was always 0 because the area below cancelled with the area above. But once again, if we happen to notice a horizontal shift, so we've got this odd function that's been shifted c units, and the limits are c minus a to c plus a. Well, again, we can now say, oh, well, that integral has to be 0. Like I say, unusual situations might never arise, but something to keep in mind. The third one may arise more often. It's a simple little integral here. If you're integrating a function from 0 to a, you actually get exactly the same answer if it's function a minus x as you do function x. Let's prove that. So function a minus x. So I'm going to do a substitution. I'll let u equal a minus x. So du is minus dx. The limits then end up swapping around. So I now have minus the integral of a to 0 of function u du. But we said the negative we can turn into a positive, swap the limits around. But because this is a definite integral, the fact that it's u is irrelevant. I could put any pronumeral I like in there. For instance, say x. So it has to give the same answer as the integral from 0 to a of function x dx. Another thing to keep in mind when we're playing with symmetry, remember if it's the same type of function when you multiply them together, then they become even functions. But if they're different types, so one's odd, one's even, then we end up with an odd function overall. So we get something like this, sine cubed. Now we could waste a lot of time here and use our technique for integrating sine cubed. I mean, it would work. But if you notice that that is an odd function, because sine cubed, well, sine is an odd function. So odd times odd times odd. Well, odd times odd, that's even because it's the same type of function. But then you're going even times odd, oh, well, that's odd because they're different types of functions. I have symmetry in an odd function, so I know that has to be 0. Here's where that last theorem works nicely. See, at the moment, that's a tricky little integral to do, x squared root 1 minus x. But I notice the limits are going from 0 to 1, and 1 happens to be the number in that square root sign. So I can change it to that. Everywhere I see x, I replace it with 1 minus x. That's what basically the rule is saying. It works nicely when that number is the same. Incidentally, it doesn't have to be the same. I mean, I could, if it was going from 0 to 2, I could still go everywhere I see x, I'll replace it with 2 minus x. It just wouldn't be beneficial. And this is where it is beneficial. Because now look at what we've got. We've got something we can expand out and integrate nicely. Add 1 to the power over the power, substitute in, we have our answer. Improper integrals. What is an improper integral? It's where you're integrating and there's some discontinuity or something like that involved. So it's not really a proper integral because really we shouldn't be integrating over discontinuities. I mean, it's not a good thing. We need to use limits and then a solution may not exist, but we'll be able to investigate. So let's have a look at our hyperbola. Imagine if we wanted to find the area from 0 to 1, but of course there's a discontinuity at 0. So really the way I should write this is the limit as n approaches 0 going from n to 1. And then we can investigate what happens in that limit to see whether we get an answer or not. Well, that's a log function. So sub in 1, sub in n, I end up with minus log n as n approaches 0. But hang on, the log of 0 is undefined. So this one's still no good. We cannot get an answer for that one. It's undefined. One like this, though, is a different story. If you had x e to the minus x squared and you're going from 1 out to infinity, so you're keeping on going forever, you would think that area would have to be an infinite area because it just keeps going and going. But we rewrite it like this. The limit as n approaches infinity of 1 to n of x e to the minus x squared. Now, x e to the minus x squared I can integrate, and that's e to the minus x squared. Substituting the n, substituting the 1. E to the minus n squared as n approaches infinity. So we have got e to a negative power. N squared is always going to be positive, so we know that power is negative. So it's our backwards exponential, if you like. Well, let's think of what that curve does. As n approaches infinity, that curve is approaching 0. So that would be the limit. Therefore, I'm just left with the minus a half times minus e to the minus 1. 1 on 2e. It actually has a definite area. So you've got this, what looks like would be an infinite area, but you actually get a finite number for the answer for that area. Area and inequalities, this idea of trapping to come up with an answer. And it comes from this idea that, hey, if you've got 3 functions, but you know that the g function is always below the f function, which is always below the h function, then when I integrate, those inequalities will stay the same. Because the area under the lowest one must be the smallest area. The area under the middle one would have to be the second biggest area, and so on. So here's an old question. They've given us a curve there, y equals 1 on x, and they've drawn a nice little rectangle for us. We can see the outer rectangles and the inner rectangles. We're going to show this expression. So they've given us a bit of an idea of how to do it. We're going to use rectangles and see what happens. I'll start with that idea then that we're going to use. The area of the inner rectangle will be less than the area under the curve itself, which will be less than the area of the outer rectangle. The inner rectangle, well, the width is, I think it was 1, wasn't it? And then the height would be the function value, so that's 1 over n. And on the right-hand side, the outer rectangle, the width was also 1, but the height would be 1 over n minus 1. And in the middle, it would be whatever that integral turns out to be. So let's work it out. Again, we've got a log function. So I can sub into the log function. I now have 1 on n is less than n on n minus 1 is less than 1 on n minus 1. I'm looking at what the answer is, and I want to play around with it a bit. I multiplied everything by n. Now, why did I do that? Because in what we're heading for, you see how 1 minus 1 on n is to the power of n? So in the middle one, I want to get power of n in there somehow. Well, how can I do that with logs? Well, if I got n out the front of the log, I now know I can bring that in and make it the power of n. So that seemed like a sensible thing to do. We'll multiply by n. Now, here's the thing. Our exponential curve is continually increasing. So as the x values go up, so do the y values. So I can say, hang on, I'm going to use my curve y equals e to the power of x here. These 3 things are x values. If I substitute them in, I'll get y values, but that order for the inequality will stay the same. So I can do that because the curve is increasing that I'm substituting into. So I end up with e to the power of 1, e to the power of log, but e to the power of log cancels, and then the last one becomes e to the power of n on n minus 1. So that's how I get the e in there. It's not quite what they wanted. So I'm going to play around with this a bit. I have turned everything upside down. Now, why did I do that? If you look at the middle term in that inequality, it was 1 minus 1 on n. The denominator just had one thing in it, and that was n. What I've got at the moment, the numerator has one thing in it. So I wanted to turn that fraction upside down. When you turn inequalities upside down, remember, the signs change. Well, we've now got our answer because all I have to do is put it in the correct order because we don't write inequalities like that. That's ugly. And now that 1 on e, which is, by the way, e to the negative 1, which is what we wanted, and on the left-hand side, e to the power of n on n minus 1 is the same as saying e to the negative n on n minus 1. And in the middle one, n minus 1 on n, well, that is 1 minus 1 on n. We have what they wanted to prove. Okay, so here's how we finish off. In the sheets, I think I've given you the old Cambridge there, but you'll notice they use 2a minus x in their formula instead of a minus x. but then they say they've shifted to A on 2 instead of shifted to A. I don't know why they do it that way. 4 i's in our book, and then of course there is the 100.